This video is going to show you how to assign mean atomic number, or MAN, background fits for calculating the background based on a single point on peak measurement versus high and low peak. If you're not familiar with mean atomic number backgrounds, I suggest you check the description for links on more information and or some videos on this channel that will go into more detail. So I've already collected my standard intensities. I have several elements here that have mean atomic number background specified. I've collected the intensity on those standards, several repeats of each of these standards. Now I need to go in and clean up those MAN backgrounds and eliminate any spurious analyses from them and make sure I have a good fit. And for example, if we go up here and we look at this willastonite, and I hit analyze, I have not messed with the barium mean atomic number backgrounds yet. And you can see that I'm getting negative 1500 ppm barium. So there's obviously a problem with my mean atomic number background fits, and I need to go in there and assess the damage. So to do that, we're going to come over here to analytical, assign MAN fits. Now, if you're starting from scratch or you've imported a method via file setup from another method, you might want to do this clear all MAN assignments, and that will just clear out anything and set everything to the default properties, and you can start from scratch. I'm not going to do that because I have done a little bit of the MAN fits already, so we're just going to go to assign MAN fits. At this point, PFE is going to load all the standards and bring up the mean atomic number background dialog. And that's what this looks like. So we're going to drop down here to barium, which is a trace element. And you can see I've got a pretty decent fit on all of my other elements, the major elements. This is a feldspar routine, and we're measuring barium. But you can see there's some major problems with barium. So you can see why I am overestimating the background and getting a negative value like you see here. I've got some samples that are pulling my fit way up off of what is probably the line. Now, probe for EPMA is pretty smart, and it knows to exclude anything that has the element of interest in it. So there's barium in this orthoclase that's specified in the standard database. Benitoite is a barium major element barium mineral, barite, of course, and this microcline. They all have specified barium. But PFE can't deal with a barium contamination or content if it's not specified, and that often happens when we're measuring trace elements. Probe standards, generally speaking, have been characterized for their major and minor elements, and uh, trace elements have not really necessarily always been accounted for. So we may have barium that is not part of the standard database, even though the sample may contain that. Also, PFE can't handle interferences. How is it supposed to know all of the possible interferences in every standard? So in this case, we have these three samples, 20, 22, and 31, that are all way above the line, double, triple, quadruple the intensity that would be expected if they did not have any barium in them. Turns out the common thread here is that we have sphene, rutile, and strontium titanium oxide. All three of those phases have a high concentration of titanium. And it turns out that titanium is a peak-on-peak interference for barium. It's very close to the same position as the barium peak. And so what we're seeing here is not actually barium, it is false barium as a result of a titanium interference. So we obviously want to get rid of those. In order to get rid of any samples from the list here, blue means it's selected, white means it's disabled. We're just going to control click. So I'm going to hold down control, click on my sphene, my rutile, and my strontium titanium oxide to get them out of that fit. Now I'm going to hit update fit. And you can see that now my curve is pretty darn good once I've eliminated that titanium interference. But you can see down here that number 412 is sitting quite a bit above the line as well. So what's the deal with it? Let's scroll down to look at 412, and that is an anorthoclase, Kakanui anorthoclase. And it turns out that that sample probably has barium in it. It's a feldspar, it's sodium rich, it's very likely to have barium in it, even though it's not specified in the standard base. If it had standard database, if it had been, PFE would have excluded it. So we're going to exclude that one. And When in doubt, I tend to do that for any samples that I'm suspicious of, even if they may or may not fall on the line. So I'm going to go ahead and get rid of that albite. That potentially could have some small amount of barium in it. The labradorite certainly could, and the anorthite probably does not, but you know, it's better safe than sorry. So I'm going to get rid of all of those. And now I just need to hit update fit. And you can see I have a nice tight line that is going to be a good fit for my barium background subtraction. Last couple points, I almost always use this Z fraction Z bar for average Z. You can see that it kind of cleans up the fit, especially at higher masses. So I leave that going. Sometimes I'll use the forced straight line fit as well, if only just to see a better representation of what sort of the straight line is. It is not mandatory, although you should have a pretty straight line if everything's in good order, at least across a narrow Z range. It should approximate linearity. So those are a couple of things that I almost always have checked. Again, I almost always use correct for continuum absorption as well. I do not know that I've seen a situation where that is not an advantage. So those are just some of the features. So now that we've got our barium fit here, let's go back to our wollastonite, which should have almost none barium in it theoretically. So hopefully we'll get a number that's much closer to 0 than 1500, minus 1500 ppm. So I'm going to hit analyze. And you can see I'm now down to minus 30 or 300 ppm. So that's a much better fit. Although there is some issue here, and I would probably, if I was working on low-level trace element barium, I would go into a little more sleuthing to see if I could get that much closer to 0. But in this case, now you know how to use and assign mean atomic number fits.